You think you know what an earthquake is. Tectonic plates colliding, the ground cracking, the earth opening up. You've seen it in movies. You've read it in a textbook. You've heard it on the news. Richard Feynman had a name for this. He called it knowing the name of something. And he spent his entire career warning that this kind of knowledge is the most dangerous thing in science, because it feels real, it feels sufficient, but it is completely empty. Feynman used to say, when you can name something, it doesn't mean you understand it. Today, I'm going to apply Feynman's method to earthquakes. I'm going to show you that almost everything you think you know about them is wrong. Not just a little wrong, but fundamentally, structurally wrong. And by the time you reach the end of this video, you'll have a new picture in your head. A picture that Feynman would recognize as correct. A picture made of real physics, not movie metaphors. Get ready to trade the picture you carry for a better one. Feynman was born in 1918 in New York. He won the Nobel Prize in Physics in 1965 for his work in quantum electrodynamics. He taught at Caltech for decades. He investigated the Space Shuttle Challenger disaster in 1986, and live in a U.S. congressional hearing, he dipped a piece of rubber in ice water and showed how the failure had happened, with a simple physical demonstration, while NASA engineers were spinning their wheels in technical jargon. That moment sums up who Feynman was. He didn't tolerate memorized explanations. He hunted for the real mechanism. He wanted to know what was really happening in the physics, in the atoms, in the electrons, not what seemed to be happening on the surface. He had a phrase that I'm going to repeat more than once in this video. The first step of scientific thinking is to question what you think you know. That's what we're going to do with earthquakes. Because when you apply Feynman's method to this subject, when you stop memorizing and start asking, but what is really going on here? What emerges is a completely different story. A story of elastic energy, of wave mechanics, of mathematical chaos, and of one of the most impressive scientific feats in human history: the ability to see inside a planet without drilling into anything. Feynman wasn't a geologist, but the physical principles he taught for decades, the ones in his famous Feynman lectures on physics, are exactly the principles that explain why the ground shakes, how this energy travels, and why it is mathematically impossible to predict when the next big earthquake will happen. If you want to understand earthquakes for real, you have to go through Feynman. So, let's get started. Before I explain what an earthquake actually is, I need to undo the image you probably carry around. Picture the scene. Two massive tectonic plates moving slowly, and at some point they collide, and the ground cracks, opens up, and the earth shakes. Maybe you imagine the ground literally splitting apart, a fissure opening up, like in disaster movies. That image is wrong. In almost every important aspect, it is wrong. First, tectonic plates don't collide the way you imagine. They slide. The main movement in active geological faults, like the San Andreas Fault in California, is horizontal, not head-on. The Pacific plate slides northwest relative to the North American plate. It's not a head-on collision. It's a very slow scrape. Second, the ground doesn't crack during an earthquake the way you visualize it. That dramatic fissure that opens up and swallows cars? That happens in specific and extreme cases, usually on the surface. What causes the shaking isn't an opening. It's exactly the opposite. It's a sudden release of energy stored over decades. Third, and this is the most important one, an earthquake is not an event that happens the moment the ground shakes. The earthquake begins long before, silently, while the rock stores elastic energy for years, decades, sometimes centuries. The tremor you feel is just the final instant of the release. Feynman used to say that most people carry mental images of physical phenomena that act as shortcuts, and that these shortcuts are invariably wrong when you ask what is happening mechanically. The earthquake is a perfect case of this. So, what is really going on? To answer that, I need to tell you about Harry Reid, the 1906 earthquake, and the concept that geophysicists call the elastic rebound theory. On April 18, 1906, at 5:12 a.m., San Francisco was destroyed by an earthquake with an estimated magnitude of 7.9. About 3,000 people died. The city burned for 3 days. It was one of the greatest urban catastrophes in American history. For science, it was a brutal and revealing opportunity. A USGS geologist named Harry Reid spent years analyzing what had happened along the San Andreas Fault. He measured the land displacements. He compared the positions of geographical landmarks before and after the earthquake, using data from topographic surveys that existed from previous decades. And in 1910, he published what would become the foundation of the modern understanding of earthquakes, the elastic rebound theory. What Reid discovered is elegant, and once you understand it, you never look at earthquakes the same way again. Rocks aren't rigid. They seem to be. But on a geological timescale, they behave like elastic materials. As tectonic plates move, slowly, centimeters per year, the rock along a fault begins to accumulate elastic strain. Think of a rubber band being stretched. It yields, it bends, it stores energy. Rock does exactly that. It deforms, and throughout this process, it stores a colossal amount of energy. But there's a limit. At some point, the accumulated stress overcomes the frictional force holding the two sides of the fault together. In that instant, the fault slips, and all that elastic energy stored over decades is released at once, in a matter of seconds. It's the rebound. The rock doesn't crack, it snaps back. Like a rubber band you let go of, like a spring you compressed and released. The San Andreas Fault is approximately 1,300 kilometers long. In 1906, about 470 kilometers of this fault slipped at the same time, in roughly 30 seconds. The energy released in that instant was absurd. And realize what this means. The 1906 earthquake didn't begin in 1906. It began decades earlier, the moment the rock started accumulating stress. The event on April 18th was just the instant the system reached its limit. Feynman would have loved this physics. It's a system of storing and releasing energy. It's classical mechanics on a geological scale. And it's completely different from the image of plates crashing together that most people carry around. One last thing about faults. They aren't cracks. That's another flaw in the popular image. A geological fault is a zone, sometimes kilometers wide, of fractured, pulverized rock, altered by centuries of movement and stress. It's not a clean line in the ground. It's a region of geological weakness, and the movement during an earthquake can occur on multiple planes within that zone. Now that you have the right mechanism, elastic energy stored, then suddenly released, the next question is, what happens to that energy after the release? When the fault slips and releases elastic energy, that energy doesn't just disappear. It propagates, and it propagates as waves. Seismic waves, which travel through the Earth in all directions, exactly like sound waves traveling through the air. Feynman dedicated entire portions of his lectures to waves. He used to say that waves are the universal language of physics, and that if you truly understand waves, you begin to understand optics, sound, electromagnetism, quantum mechanics. Earthquakes are a wave problem, and the behavior of these waves reveals things about the Earth that no drilling instrument could ever discover. There are two main types of seismic waves that travel through the Earth's interior. The first type are P waves, primary or compressional waves. They work like sound waves. They compress and expand the material in the direction they are traveling. They are the fastest, reaching between 6 and 8 kilometers per second in the Earth's crust. They arrive first at the seismograph. They can travel through both solids and liquids. The second type are S waves, secondary or shear waves. They make the material move perpendicular to the direction of propagation, like a rope you shake from side to side. They are slower, between 3.5 and 4.5 kilometers per second. They arrive after the P waves. And here is the detail that changes everything. S waves cannot propagate in liquids. This isn't a minor technical detail. It's one of the most important discoveries in the history of geophysics. When seismographs around the world recorded earthquakes, scientists noticed something strange. There is a region on the opposite side of the Earth where S waves simply don't arrive. It's as if there were a seismic shadow, a zone of silence where the S waves were blocked while traveling through the planet's interior. The explanation is straightforward. If S waves don't travel in liquid, and if they are being blocked before crossing the Earth's interior, then the Earth's interior has a liquid region. The Earth's outer core, a layer that begins at a depth of approximately 2,900 kilometers, is liquid. Mostly molten iron and nickel. We know this not because someone drilled down there. The deepest humanity has ever drilled was the Kola super deep borehole in Russia, 12.2 kilometers. Less than 0.2% of the Earth's radius. We know the core is liquid because earthquakes sent seismic waves to the four corners of the planet. And those waves behaved in a way that only makes sense if there's liquid inside. There is also a similar discovery for the inner core. P waves arrive at the opposite side of the Earth with a certain delay from a specific angle, which suggests that, inside the liquid core, there is a solid sphere. The inner core, also solid, mostly made of iron, but compressed by the colossal pressure of the entire planet above it. All of this, the entire internal structure of the Earth, was inferred from how seismic waves behave. A Croatian geologist named Andrija Mohorovičić discovered, in 1909, the discontinuity that today bears his name, the Moho, simply by observing that seismic waves accelerated at a certain depth. That meant they had entered a different material. This transition marks the boundary between the Earth's crust and mantle. Seismic waves are the planet's X-rays. And Feynman would have loved exactly this, the idea that we can see the invisible indirectly, through the behavior of waves. It's the same principle that allows a doctor to see your bones without opening up your body. Except in this case, the body is 12,742 kilometers across. Now I need to talk about the number you see on the news when an earthquake happens. Magnitude 7.1. Magnitude 9.0. You probably think you know what that number means. You probably think it's a scale from 0 to 10 where 10 is the worst possible, and that a magnitude 8 earthquake is roughly twice as strong as a magnitude 7. You are completely wrong. And this is exactly the kind of trap Feynman loved to identify, when people's linear intuition meets a logarithmic scale. Let's start with the history. In 1935, a seismologist named Charles Richter at Caltech, the same university where Feynman worked, created what became known as the Richter scale. But what many don't know is that Richter created this scale specifically for Southern California, specifically for earthquakes of magnitude between 3 and 7, and specifically using a specific type of seismograph, the Wood-Anderson. The scale was designed for a very particular context. The problem is that it leaked to the media and became the popular worldwide standard. Today, science uses the moment magnitude scale, or MW, which was introduced in 1979 and is the current scientific standard. It measures the total energy released by the earthquake more accurately, especially for large events. But what really matters is understanding what these magnitudes mean in terms of energy, because this is where human intuition fails catastrophically. The scale is logarithmic. Each unit of magnitude corresponds to an increase of roughly 31.6 times in released energy. Not 10 times, not 2 times, 31.6 times. Think about what that means in practice. A magnitude 5 earthquake releases about 31.6 times more energy than a magnitude 4. A magnitude 6 releases 31.6 times more than a 5, and roughly 1,000 times more than a magnitude 4. And a magnitude 9 releases roughly 1,000 times more energy than a magnitude 7. 1,000 times more. Not a little bit bigger, not twice as strong. 1,000 times. The Tohoku earthquake in Japan in 2011 was a magnitude 9.0. The earthquake that struck Haiti in 2010 was a magnitude 7.0. On the popular scale, one number is smaller than the other. It seems like we're comparing reasonably similar things. In real physics, the energy difference is 1,000 times. Feynman had a way of attacking this problem. He said that the human brain evolved to perceive the world linearly, more or less proportionally. You have 2 apples, I have 4, the difference is clear. But the universe frequently works on scales that are not linear. And when linear intuition meets logarithmic reality, intuition loses every time. The seismic scale was designed by scientists for scientists, in logarithms, because the energy spectrum of earthquakes is so vast, from a tiny microtremor to a continent-moving event, that a linear scale would be impossible to use. But when this scale reaches the news without explanation, it creates a false sense of comparability. The journalist who says, "Today's earthquake was a 7.1, while last week's was a 6.9, is describing, without knowing it, an energy difference of roughly 2.5 times. It's not a journalistic detail. It's a difference that completely changes the level of possible destruction. Understanding logarithms is understanding how the universe actually organizes its phenomena. And this is one of the greatest services Feynman provided to science education, making it obvious that scale matters, that math matters, and that trusting intuition without mathematical verification is a trap. Now we arrive at what is perhaps the most uncomfortable revelation of this video. More uncomfortable than the wrong image? More uncomfortable than the logarithmic scale. Because this one involves not just what people get wrong, but what people expect from science. The question everyone asks, why can't scientists predict earthquakes yet? The answer people usually have in their heads is because the instruments still aren't good enough, because computer models still aren't powerful enough, because science is still working on it. That answer is wrong. And the reason it's wrong is one of the deepest problems in modern physics: chaos theory and sensitive dependence on initial conditions. I'll explain what this means in practice, using the reasoning Feynman applied when he encountered this type of problem. To predict an earthquake, not in the next few seconds, but in the next days or weeks, you would need to measure the stress state of every fault segment with perfect precision. Not approximate, perfect. Because the process by which an earthquake initiates, called nucleation, involves phenomena that occur at the scale of rock crystal grains, microstructures at the millimeter scale that interact in ways that no sensor could ever completely measure. And here lies the fundamental problem. Chaotic systems, systems where future evolution depends sensitively and non-linearly on initial conditions, are mathematically unpredictable beyond a certain time horizon. Not because the instruments are bad, but because the system itself amplifies uncertainties. A tiny difference in initial conditions, smaller than any instrument could detect, leads to completely different outcomes. The atmosphere works like this. That's why weather forecasting has a natural limit of about 2 weeks, no matter how much computing power you use. The system is chaotic. Earthquakes seem to work the same way. The exact boundary between a fault that will slip now and one that will keep building up stress can depend on factors: fluid pressure in the fault, microscopic distribution of fractures, local temperature, that are impossible to measure with the necessary resolution. This is not a failure of science. It's a mathematical property of chaotic systems. Feynman used to say something important about this. He warned against the mistake of confusing the fitting of mathematical patterns with causal explanation. You can take historical earthquake data, apply sophisticated algorithms, and generate predictions that seem reasonable, without it meaning that you actually understand the real mechanism. The pattern is not the mechanism. What science can do, and does very well, is statistical probability. Seismic risk maps show regions where the probability of a major earthquake in the next X years is Y%. That's honest. That's useful. But it's not a prediction in the popular sense. There's also a crucial distinction that the news often confuses: the difference between early warning and prediction. Early earthquake warning systems, which exist in Japan and, in a more limited way, in California, work by detecting P waves, which are faster but less destructive. When the system detects a significant P wave, it sends out alerts before the S waves, the destructive ones, arrive. Depending on the distance from the epicenter, this gives anywhere from a few seconds to about a minute of warning. That's not a prediction. It's real-time detection. The difference is fundamental. And what happens after a major earthquake? Aftershocks, the secondary tremors that continue for hours, days, sometimes years. They also follow a fascinating mathematical pattern described by Omori's law, formulated in 1894 by the Japanese seismologist Fusakichi Omori. The frequency of aftershocks decreases roughly as 1 divided by time. A power law distribution, not a normal distribution. This is important because power law distributions are the hallmark of systems operating in critical states. Systems that, as Feynman would note, exhibit scale-invariant behavior. There is no natural scale for earthquakes. A large earthquake and a small one are generated by the same kind of process, just on different scales. This mathematical property of earthquakes, which Feynman would immediately connect to criticality and statistical physics, is part of the reason why detailed prediction is so difficult. There is no sharp boundary between the event that won't happen and the one that will. Going back to something I mentioned about seismic waves and the Earth's interior, because this is one of the most extraordinary stories in modern science, and it deserves its own chapter. Consider this fact. The deepest hole humanity has ever drilled into the Earth's crust was the Kola Super Deep Borehole on the Kola Peninsula in Russia. The Soviets started drilling in 1970 and kept going for decades. In 1994, when the project was shut down, the hole was 12.2 kilometers deep. That's an impressive feat of engineering. And yet, it represents less than 0.2% of the Earth's average radius, which is 6,371 kilometers. We've never come anywhere near the mantle. We've never reached the Mohorovicic discontinuity, which under the continents sits between 30 and 50 kilometers deep. Our most ambitious drilling instrument in history didn't make it 1% of the way to the center. And yet, today, we have a detailed model of the Earth's entire interior. We know the thickness of the crust at different points. We know where the mantle begins, where it ends. We know that the outer core is liquid, and the inner core is solid. We know the velocities of seismic waves in each layer, which tells us the composition and physical state of the materials. How do we know all this? Through seismic waves from earthquakes. This is what seismologists call seismic tomography. The same principle as a medical CT scan, but using the entire Earth as the patient and earthquakes as the X-ray source. When an earthquake happens somewhere on the planet, its seismic waves travel in all directions, refracting and reflecting at the boundaries between layers of different densities and compositions. Seismographs around the world record the arrival of these waves with millisecond precision. By combining the records of thousands of earthquakes picked up by thousands of seismographs over decades, scientists are able to reconstruct the three-dimensional structure of the entire Earth's interior. Mohorovičić did the initial version of this in 1909. Observing that seismic waves from a local earthquake arrived faster than expected at certain distances, he concluded that they must have been deflected by a denser layer below the crust. He found this boundary at roughly 54 kilometers deep in the Balkan region. The Moho discontinuity, as it's called today, marks the boundary between crust and mantle across the entire planet. Discovered not with a drill, but with the mathematics of waves. Feynman had a particular fascination with indirect measurements. He used to say that the most elegant measurements in science are those that reveal something you can't see directly, by inferring from phenomena you can measure: the speed of light, the mass of the electron, the structure of the atom, all inferred indirectly, through clever experiments. The structure of the Earth's interior follows exactly the same principle. Every earthquake that happens somewhere in the world is, at the same time, a human tragedy and a geophysical experiment. The waves it sends through the planet carry information about every layer they pass through. And seismologists, with decades of accumulated data, have learned to read this information with astonishing precision. It's like listening to the sound an object makes when you tap it, and determining, by the way that sound resonates, what's inside. Except the object is nearly 13,000 kilometers in diameter, and the sound travels at several kilometers per second. There is one aspect of Feynman's method that I find more important than any specific fact he discovered or explained: his honesty about the limits of knowledge. Feynman used to say that it's better to have questions and not know than to be certain of something that is wrong. He considered honest uncertainty to be an intellectual virtue, not a weakness. And when we apply this principle to modern seismology, we arrive at a set of questions that science still can't answer with precision. The first unsolved problem is nucleation. We know how earthquakes propagate after they start, but the exact moment a fault transitions from accumulating stress to slipping, the microscopic trigger, is still not fully understood. Why do certain fault segments slip smoothly and continuously, while others accumulate stress for centuries and then release it all at once? The physics of this process at the scale of rock grains is an active frontier of research. The second problem is remote triggering. There is evidence that large earthquakes can trigger seismic activity on other faults at distances of hundreds or even thousands of kilometers, distances where the additional static stress is minuscule. How can the seismic waves from a large earthquake destabilize faults that are so far away? Proposed mechanisms exist, but the details are still debated. The third problem is the role of fluids. Water and other fluids present in fault zones profoundly affect seismic behavior. Fluid pressure can reduce friction on faults and facilitate slipping. This is relevant not only for natural earthquakes, it's the mechanism by which wastewater injection into disposal wells can cause human-induced earthquakes, as has been documented in oil and gas exploration regions in the United States. The fourth problem is the issue of foreshocks. Some large earthquakes have detectable foreshocks, minor seismic activity that precedes the main event. Others don't. We still don't know, looking at a foreshock in real time, whether it's a foreshock of something huge or just an isolated small earthquake. The information asymmetry is frustrating and real. Feynman would have approved of this kind of honesty. He said the first step to solving a problem is admitting you don't know the answer, not pretending to know more than you do. The frontier of scientific knowledge about earthquakes isn't a failure. It's where science truly begins. And the fact that these questions remain open is an invitation, not a defeat. So, what is the correct picture? The one Feynman would recognize as true? Earthquakes are systems of storage and release of elastic energy. Rocks, subjected to the forces of tectonic plates, deform slowly over decades and centuries, accumulating stress like a compressed spring. When the stress exceeds the fault's friction limit, the rock suddenly slips, and all that accumulated energy is released in seconds, propagating through the planet in the form of seismic waves. These waves travel through the Earth at speeds of kilometers per second, refracting and reflecting at the boundaries between different materials. Their behavior reveals the complete internal structure of our planet, layer by layer, without needing a single drill hole beyond the 12 kilometers we've already done. The energy released follows a logarithmic scale that breaks human intuition. One step on the magnitude scale represents almost 32 times more energy. Magnitude 9 versus magnitude 7. 1,000 times more energy. Not twice. 1,000. Precise prediction days or weeks in advance is likely mathematically impossible. Not an overcomable technological limitation, but a fundamental property of chaotic systems where small uncertainties in initial conditions amplify non-linearly. What science honestly offers are probabilistic hazard maps and early warning systems of seconds to minutes. And there are genuine frontiers of knowledge: nucleation, remote triggering, the role of fluids, where the questions are still open. That is what Feynman would call truly knowing an earthquake. Not memorizing a name, not repeating a movie scene, but understanding the mechanism, where the energy goes in, where it stays, how it gets out, how it travels, what it reveals. This method, discarding the wrong picture, going back to the physical mechanism, being honest about what you don't know, is Feynman's most enduring legacy, and it works for any science subject you want to apply it to. The next time you hear magnitude 7.2 earthquake, you won't think about the ground cracking open. You'll think about elastic energy being released, about waves traveling at kilometers per second, about S-waves that stop in liquid and reveal a molten core deep inside, about decades of tension unleashed in 30 seconds. That is the accurate picture. Stranger than the wrong one. Richer than the wrong one. And true. If this kind of physics interests you, if you like it when the popular image of a phenomenon gives way to real physics, leave a like and subscribe to the channel. We'll keep applying this method to other topics, where what seems obvious is completely wrong.